This is Unit 1, Specimen Paper 2, in question 12. Light from a sodium vapour lamp passes through the slits in a diffraction grating. So you've done this and creates a pattern, and it's called the emission spectrum. And the property of light which produces the pattern, you might be tempted to say diffraction, but it's not on the list, so you can't say that. It's not absorption, or else we wouldn't have the pattern. Interference, that's the answer. Reflection will like to come backwards on yourself rather than be on the screen. And refraction, that's just the bending of light. So the answer is interference. And when we draw the diagram in a minute, you'll see what we're talking about. For a clear diffraction pattern to be produced, the light needs to have coherence. So it's just another definition that you need to learn. So coherence must have the same wavelength or frequency. So two waves is one wave. If I had another wave, it might be a different wave. Not very good, but you can see there that the wavelengths are the same, and if this was time, the frequencies would also be the same. We could also draw another wave that went like this, possibly. Not a brilliant drawing, but you can see there. But you can see the peaks are with the troughs, but it's still got the same wavelength. So if the wavelength is that's the same as the wavelength there. So it's still coherent even though it's in antiphase. So must have the same wavelength or frequency, or must have a constant phase difference. So constant phase difference, and you can see there in the diagram. So those, if you're not sure about those, don't just write them in like I have. But you look and see what this means. Go and look at it and Google up some get some Google images up, constant phase difference, some examples. And then we've got 4 marks for explaining how a diffraction grating produces an emission spectrum. You could use a labelled diagram. I would definitely use a labelled diagram here. So the key text, and then I'll draw the diagram. So the light contains many wavelengths. We know that. So light contains many wavelengths, and so light gets diffracted in all directions when it leaves this grating. So light gets diffracted or travels in all paths. You'll see this in a minute. All paths or directions when it leaves the grating. Right. So let's just draw a diagram, shall we? So I'm just going to draw a simple kind of grating, the classic kind of double double slit experiment where you've got waves travelling towards this grating, and then we're going to get diffraction happening. So the waves will start to do that. The wavelength will still be the same, so I'm trying to draw these with the same distance between the wave fronts. And we're getting points where these waves are now crossing over each other, and so we're going to get interference. Put one more on. I've probably drawn them a bit too close to the actual grating itself. So we're going to get points where we're going to get constructive and destructive interference. So this point here, we've got two wave fronts. So this point here, we've got two of those kind of waves. And that's going to equal 1 twice because I'm a superposition. And that would also happen. Here. What we've got is just the other way around. So we've got again two troughs. So that would, again, I have to draw this on top in a moment, twice as big, yeah. But the interesting place really is here, where we've got a wave front, we've got a crest and a trough. So we've got one wave there, and we're adding to it. Not the same one, but that one's, instead of going up, it's going down, then up, down, and that will equal this destructive interference. So we just need to put that into words. So we get different paths, so different path differences. So we get different path differences. Which means we get a phase difference. So a phase difference here. And if the phase difference is kind of half a wavelength, then they'll cancel out. So here, phase difference equals half a wavelength. So they're kind of half out of phase. So that is our destructive and destructive interference. So if phase difference is half wavelength, that equals destructive interference. So they will cancel out. So we'll cancel out, there we are. And then the last one is describing one of these situations here that I've drawn in the red or the blue. So if the difference is a wavelength, so these are exactly a wavelength, in phase or exactly away, out of phase, but exactly where, so back in phase again. Then we've got constructive interference. So phase difference equals a wavelength. That is now constructive interference. So if phase difference is a wavelength, then waves add up, or a better thing to say, constructive interference. Constructive interference. But the diagram, if you drew it, I'm sure they would give you marks if you drew this sort of diagram to help you.